Okay, welcome back once more, everybody. I'll just mention about the assignments. So the third assignment was due, I think, yesterday. I noticed a couple people did not submit it. So if you just don't want to do it because you don't have the time, that's no problem. But if you do want to do it still, if you need just a couple days extension or something, just let me know and you can still hand it in. I haven't posted solutions yet, so if you can do it, but you just to get around to it, you can take a couple days. The fourth assignment has now been posted. I just posted it this morning. And that's due basically a week from now, Monday at 11:59. And so what we're going to do is we're going to have a regular class today, regular class on Thursday. Then on Tuesday, I'm going to do a review for the midterm, and then the midterm is next Thursday. And I'll also try, as I did for the first midterm, to post some practice problems to help you prepare. The first midterm was pretty well done, so it seemed like maybe the practice problems were useful, so I'll try to do that. Okay. For people that just walked in, I just wanted to mention that the third assignment was due yesterday, but in case you didn't hand it in yet, you need a couple days, that's fine too, just let me know. Okay, also I'll just ask it at the start. So we're going to talk about sound waves today, and we're really going to get into the equations that specifically govern sound waves. So far we've been sort of talking about fluid mechanics in general, and today we're going to focus on a specific phenomenon of sound. Does anyone know what the speed of sound is in air, roughly speaking?
343.
343, exactly. Yeah, that's right. So it's pretty fast, 343 meters per second. And in this class, we'll derive that from first principles. We're going to get a formula that gives that answer. Okay. So last time we did two main things. The first thing is we finally closed our system of equations. So for several classes now, we've been grappling with the fact that we seem to have too many variables in our system, dynamical variables, so things like velocity, pressure, density, possibly temperature, depending on how you're counting. But not enough equations. We had the momentum equation and the mass continuity equation, but that only gave us 4 equations total, 3 from momentum, because it's a vector equation, and then 1 from mass continuity. But we had at least 5 variables. We had 5 variables, u, v, w, the velocity components, pressure, and density, but we only had 4 equations. And we argued that every equation in fluid mechanics comes from a conservation principle in physics. So the momentum equation comes from conservation of momentum, which we also call F equals ma, Newton's second law. Mass continuity comes from conservation of mass. And then the other thing that we hadn't used yet until last class really was conservation of energy. So energy is also conserved, at least in classical physics. And so we added an energy equation. So that was involved a little bit of thermodynamics. I just sketched out the thermodynamics. So what I said was basically, what we invoked was the first law of thermodynamics, which says that the change in energy of an ideal gas in this case is equal to the little bit of work done, the pressure work plus the heating. We made the argument that in something like a sound wave, the physics is happening very quickly. So in normal sound waves in air, usually everything is oscillating hundreds of times per second, and the conduction of heat, molecular diffusion of heat, operates very slowly. So we can basically ignore that for the purpose of sound waves, which is the equation dq equals 0. That says that there's no heat energy moving in and out of a given parcel of gas. It only changes its energy because it's either squeezed or it expands. The internal energy of a gas is proportional to its temperature. That's basically just saying that the temperature of a gas refers to what it means is the kinetic energy of the molecules inside. And then the ideal gas law and the formula for the gas constant. And what that gave us, if you just take these 5 equations, actually you can derive this adiabatic constraint, which is that pressure is equal to a constant times the density to the power gamma. And gamma here is a pure number. That's a specific number. Gamma is equal to 7 over 5, which is exactly equal to 1.4. And so there's a direct, so normally we have the ideal gas law that links pressure, density, and temperature. But under this adiabatic assumption that there's no heat flow happening, we can actually reduce that down to this equation that directly relates pressure and density with temperature having been eliminated along the way. And that's called the adiabatic constraint. And this gave us our final equation, because now when we recount everything, we've got the momentum equation, that gives us 3 equations. We've got mass continuity here, gives us 1 more. And then the last one comes from the adiabatic constraint, so we have 3 plus 1 plus 1 equals 5. And now we have 5 unknowns, U, V, W, pressure, and density. And you could ask, what about the temperature? And basically we've eliminated temperature from the system. So if you wanted to care about temperature, you could add temperature as a variable, and then add the ideal gas law as one more equation, and that would link temperature back in. And so on the 4th assignment, you're going to have to do that. There are some questions asking you about the temperature of various things going on in the sound wave system, and so you'll have to incorporate the ideal gas law as well. So that was the first part of last class, was closing the system, so we have now an equal number of equations and unknowns, and so now we can start solving it, and that's what we're going to do today for the case of sound waves. We're going to solve for the pressure field, the density field, and the velocity field. So solve for all the fluid variables. But we also talked last time about a mathematical technique that actually allows us to do that solution. So in general, if you look at these equations, they're all nonlinear. And they're nonlinear because we say an equation is nonlinear basically when if you double all the variables, all those doublings should cancel out, or each term should basically double. But as you can see, for example, in this pressure equals rho to the gamma here, the fact that this gamma is not equal to 1, it's 1.4, means that if you double the density, you don't double the pressure. It's a nonlinear relationship. Similarly, these material derivatives have the u dot grad u term in them. That's a quadratic term. So that term is nonlinear, that term is nonlinear. This term has a product of density and velocity, that's nonlinear. And so there's all sorts of nonlinearities floating around in this equation. And that's very typical of fluid dynamics. Basically, anytime you're doing a fluids problem, it's fundamentally nonlinear. But in many, many cases, we can make an approximation that it is linear. And that's called the process of linearization. And basically, any study of waves that you've ever encountered has always basically used linearization. And even the problem of the simple pendulum, probably in maybe 1051 or 1021, if you took that physics course, you probably studied the pendulum. And actually, when we study the pendulum, we actually make a linearization approximation, because there's such a thing as the nonlinear pendulum, which is actually the more realistic version, and the pendulum that we're used to studying is the linearized version of that. And so basically, the idea is how do we transform from a nonlinear equation to a linear one? And the reason we want to do this is that nonlinear equations in general are very difficult to solve. It's possible to solve them exactly, like by hand, like write down a formula for the solution. That's possible in special cases only. And there are lots of special cases, and there are like books on like treating all the special cases. But if you get a random equation that wasn't like cooked up somehow, it wasn't like contrived to be a homework problem, most of the time it has no exact solution. On the other hand, all linear equations can be solved by classical techniques, and so there's like methods. So it's not solved via tricks. It's not like a special trick that works for a certain example. There's universal methods that will work for every equation. And so when we do this linearization, very often we can solve the equation quite easily. And that means, and the benefit of solving it is that we can analyze the solution, understand the physics, make predictions, and all those things that we want to do when we study physics. Okay, so the core concept of linearization is that in any kind of wave motion, we always think of waves as riding on some background state. So for example, for surface waves, or probably very familiar type of wave, we normally think of the ocean as got some flat surface, and then the waves are oscillating on top of that flat surface. So there's a sense in which there's a quiet background where there's nothing happening, and then the waves are superimposed on that. And the assumption of linearization basically is that we're going to assume that the wave motions, the fluctuations, are in some appropriate sense small compared to the background. And so in the case of, so we're going to do surface waves later, but just to sort of evoke the idea now, that if the size of these ripples, so the up and down, the distance, the height at which the surface is disturbed, if that height is small compared to the total depth of the ocean, which of course for basically all normal types of waves that's true, then we can make a linearization assumption and we can simplify our equation dramatically. I've drawn here the example for a sound wave. So sound waves are pressure waves primarily. And so the idea of a sound wave is that in this room, there's about 1 atmosphere of pressure. Roughly speaking, just the average Earth surface pressure, that's the pressure in this room. And then as I'm speaking or any sound is happening, the pressure is fluctuating up and down a little bit. And it kind of looks like this. If you plotted the pressure versus time, so this is the y-axis is pressure and the x-axis is time here, what you would see is that the pressure has a certain average value. We're going to call that P0, P naught. And then it fluctuates up and down a little tiny bit on top of that. But the size of those little ups and downs, these pressure fluctuations, are small compared to the absolute background pressure of just the Earth's surface pressure. And that's going to be the key assumption that allows us to turn the equations from nonlinear, which are very difficult to solve, into linear, where the analysis becomes very easy. And just last time, so we're going to do a bunch of this kind of math today, but just last time I showed an example of how this could be done. So if you start from just, this is not an equation, this is just 2 terms in the momentum equation. So we have du dt plus u du dx, so this would be the momentum equation in one dimension. So what we do is we say that our velocity here is equal to u naught, which I'm going to actually set to 0, plus u prime. And so we always denote primes mean the fluctuating part, the small part, and then the 0 part, u naught, that's the background. In the case of pressure, there's a large background pressure, the pressure of the whole atmosphere above your head. For velocity, we often consider that the background state is 0, that we have the state of rest. And so our background state is actually just u equals 0 in that case. You can also, and we'll do this later, you can think about what if the air in this room was moving at a finite speed? There was some background flow, and then there's sound waves on top of that. You can also talk about that, and that gives rise to the Doppler shift effect. And so we're going to come back to that later. But for right now, we just think of, like, let's say that the room's at rest, so it's got a background pressure, but otherwise the air is at rest. So we write u is equal to u naught, the background pressure, background flow is equal to 0, plus u prime, and we just take this expansion, u equals u naught plus u prime, and we throw it in for u, plug it in our original nonlinear equation, which is nonlinear because you have a product here of u times u. The fact that there's a derivative doesn't matter. If you doubled u, this term would double, but this term would go by a factor of 1. So we plug in here 0 plus u prime for u. And we end up, after we just cancel out the zeros, we end up with this equation at the bottom, du prime dt plus u prime du prime dx. And the whole concept of linearization is that if we think of u prime as being a small number, then this first term only has 1 factor of the small number, but this second term has 2 of them. It's a small number times a small number. So we take 2 small numbers and multiply them together, the result is even smaller than the number you started with. As we drop this term because it has 2 primes. And that's kind of the, if you in terms of like a bookkeeping method, that's how you do linearization. You plug in every quantity equals background state plus prime, then you crank through the algebra, get a bunch of terms. Some of them have only 1 prime, some of them have 2 or more. You just throw away everything with 2 or more primes, and that gives you the resulting linearized system. In this case, we just get this one term out, which is just du prime dt. Okay, and so today we're going to apply this to all of our equations and get equations for sound waves, and the sound speed is going to emerge naturally as a parameter that's already in our equations. Okay, so does anyone have any questions about the review or anything else related to the course? Okay. Okay. In that case, let's move on to sound waves. So the equations for sound waves in one dimension. So let's write down equations in 1D. So for momentum, we have du dt equals minus 1 over rho grad p. And in one dimension only, this goes to partial u partial t plus u partial u partial x equals minus 1 over rho partial p partial x. We have d rho dt, this is mass, so this is momentum, mass is d rho dt equals minus rho times the divergence of u, which in one dimension becomes d rho dt plus u d rho dx equals minus rho du dx. And adiabatic is pressure equals a constant times rho to the gamma, which is unchanged. So what we're going to do now is we are going to linearize all three of these equations, so that then we'll have a set of still three equations, but instead of three coupled nonlinear equations, they're called coupled because the same variables appear sort of randomly throughout these equations. So like the equation for pressure depends on density, density depends on velocity, velocity depends on pressure. They're all kind of interlinked like that. We're going to generate a set of three coupled linear equations, and then that will allow us to do all kinds of nice analysis and solve for things like the sound speed and so forth. Okay. So our task is to linearize these three to produce a set of three coupled linear equations. So first, we need to specify the background state. And for us, the background state is going to be the state of rest, so that there's zero velocity. But the pressure and the density aren't zero. The pressure is some background pressure, basically the atmospheric pressure, and the density is whatever the surface density of air is. And so that would depend on the temperature generally, but we're just going to assume that there's some background density. It turns out the surface density of air is about 1.2 kilograms per meter cubed. So we're going to set pressure equals pressure 0, which equals about 1.01 times 10 to the 5 newtons per meter squared, also known as 1 atmosphere. Density equals density naught equals 1.2 kilograms per meter cubed, and U equals 0. So this will be our background state, on top of which we're going to have sound wave propagation. Okay, so let's start with the momentum equation. So we have partial u partial t plus u partial x equals minus 1 over rho partial p partial x. I'm just going to pause for a second, let you guys write this stuff down. So now we're going to plug in u equals u naught, which is going to be 0, plus u prime. P equals p naught plus p prime, and rho equals rho naught plus rho prime. We're going to substitute these three expansions of everything that's being written as basic state plus perturbation, and we're going to just plug those in directly into our momentum equation. So we'll get here partial by partial t of u naught plus u prime, we get u naught is 0, plus u naught plus u prime, u naught is 0, times d by dx of u naught plus u prime, and u naught 0, equals, now stuff that's not 0, 1 over rho naught plus rho prime, times d by dx of p naught plus p prime. Okay. So something that we are going to assume in this course is that the background state, P naught or rho naught, whatever the background state is, that it's uniform in space. So it's a simplifying assumption, because if you look, for example, at different places on Earth, the surface pressure can vary a little bit, or the density can vary a little bit. But for sound waves in something like this room, the background pressure is roughly the same everywhere. And so what that means is that P naught is just a constant number. So as I've written over here, when I say P naught, I mean this number 1.01 times 10 to the 5 newtons per meter squared. So d by dx of P naught is going to give 0. Because this is just a constant, it doesn't depend on x, so when we take the derivative, that's going to vanish. And so we get here, we get partial u prime, partial t, plus u prime, partial u prime, partial x, equals minus 1 over rho naught plus rho prime times d p prime dx, because the derivative here vanishes. Okay. So right away, we can simplify a little bit. Because we're always going to drop any term that has more than one prime. So anything with a single prime is okay, we keep that, those are the linear terms. That's what's going to encode all the wave physics. But any nonlinear term that contains more than one prime, we drop that because it's quadratically small, or it's more, or it's even smaller. So this term here, the u prime du prime dx term, so this term is nonlinear. It's got two primes. So we drop this one. So we can now write our equation as partial u prime partial t equals minus 1 over rho naught plus rho prime d p prime dx. So this is already much simpler than what we started with. It's got less nonlinear terms. But it still is nonlinear, because this combination of rho prime and p prime, it's not the case that if you doubled rho prime and p prime, this term would just double. So this term is actually nonlinear. So we have to figure out how to simplify that. So so we need to simplify or linearize this term. I'm going to start that on the other board, because this one involves a little bit of a Taylor series trick. So the work that we did early in the course on understanding Taylor series is now really going to come up when we do all this linearization. So let's simplify the expression. 1 over rho naught plus 1 over rho prime, assuming rho prime is small. What we mean by that is that rho prime divided by rho naught is much less than 1. So was there a question?
Yeah. So you said the derivative of PO like vanishes. Why
Yeah.
doesn't rho O vanish too? Like, why can't we just assume that's like 1?
Here?
Yeah, I guess.
Yeah, so the reason is that P naught, it doesn't depend, so P naught and rho naught, they're both numbers that are larger than 1. But in this case, but they don't depend on space, so they're not functions, it's a constant number. So the reason that we're ignoring this is because you're taking the derivative of it. And so the derivative of any constant equals 0. But this one, if we were writing down d rho naught dx, that would also be 0. But in this case, rho naught is not differentiated.
Okay, yeah. Thank you.
So pause for that. This lecture is probably one of the more mathematically tricky lectures in the course. So I'll just ask, does anyone have any idea how we could simplify this under the assumption that rho prime is small compared to rho naught? Has anyone seen something like this before or have a guess? It's a little bit tricky, so I'm going to show it, but has anyone have an idea?
Could you just make it 0? Like, get rid of it?
It's funny, that's actually what's going to happen in the end. So so that's correct. But to understand why that's true, it takes a little bit of more math. So we're gonna look at exactly why that's true. But that's actually exactly what we're going to do. We're just going to drop rho prime compared to rho naught. But to get there, we need a couple steps. Okay. So let's write 1 over rho naught plus rho prime. And I'm going to write this as 1 over rho naught outside of 1 plus rho prime over rho naught. So all I did was I factored a factor of rho naught outside the bottom. We can write this as 1 over rho naught times 1 plus rho prime over rho naught to the minus 1 top. And now the benefit of doing this is that now we have a function 1 plus rho prime over rho naught to the minus 1 with an explicit small parameter. So this thing here is small. Rho prime over rho naught. So now let's do a Taylor series. So there's a Taylor series result. So we remember that f of x plus delta is always roughly equal to let's say f of x naught plus delta is always equal to f of x naught plus f prime of x naught times delta plus higher order terms. So this is the first order Taylor series. So in this case, we have the function (1 plus x to the minus 1) where x equals rho prime over rho naught is small. So you can think of this rho prime over rho naught as just a parameter x, and we can now write this 1 plus x to the minus 1 power in a Taylor series. So this will equal, so here basically our x naught equals 1, and our delta equals x. Does anyone happen to know the Taylor series for this function? Sorry, someone said that?
I knew it, I forgot.
Okay, well, we're going to work it out anyway, so you remember that in a second. Okay, so this always equals, so f of x naught plus delta. So we have x naught is 1, x is delta, so it equals f of x naught. So that would just be 1 to the minus 1 power, plus f prime. So f prime would be minus 1 over 1 plus x squared, evaluated at x naught, times times x. And here remember x naught equals 0. So plus dot dot dot. And so this is a little bit confusing notation. So 1 to the minus 1, that's just equal to 1. And then we have minus. When we say here evaluated at x naught equals 0, that means we plug in 0. We plug in 0 for x. And so we get here just minus 1 over, so plus minus 1 over 1 plus 0 squared times x. And so this is just minus 1 over 1. So in the end, we just get 1 minus x plus higher order terms. So the point here, the end result, is that 1 plus x to the minus 1 is roughly equal to 1 minus x. And this maybe is a formula that people, is this what you're remembering, something like that?
Something like that.
If you might have seen here 1 plus x, there's a famous formula, 1 plus x to the n is roughly 1 plus nx, is maybe the form you've seen it in. But anyway, we don't need all that generality, we just need this particular example. So, now instead of using x's and stuff, we can go back to our real variable, which is rho prime over rho naught. So based on this result, 1 plus x to the minus 1 equals 1 minus x, we can write, so 1 plus rho prime over rho naught to the minus 1 roughly equals 1 minus rho prime over rho naught. And now this is nice and simple because it doesn't have any inverse fractions or anything in it. It's just a 1 minus this term. Okay. We now have 1 over rho naught plus rho prime equals 1 over rho naught times 1 plus rho prime over rho naught to the minus 1. Approximately equals 1 over rho naught times 1 minus rho prime over rho naught. That's using this formula here. And then expanding that out, we just get 1 over rho naught minus rho prime over rho naught squared. And so this is our linearized coefficient. But now we have to plug this back into our equation. Because remember, we started from this momentum equation where 1 over rho naught plus rho prime appeared as a multiplier to p dx. So I'm going to take our formula we just derived for just this piece and plug it back in. I'll just wait for a minute there. So we can now plug this in, so plug this into our momentum equation. So we had du prime dt equals minus 1 over rho naught plus rho prime dp prime dx. And that gives us du prime dt equals minus 1 over rho naught minus rho prime over rho naught squared dp prime dx. And we can just expand that out. That's minus 1 over rho naught dp prime dx plus 1 over rho naught squared rho prime dp prime dx. So just substituting back in to what we previously had. So again, we started from the full momentum equation. We plugged in our background state, eliminated terms with 2 primes, so this term dropped right away. Then we had a little bit of a more complicated term here with the density. We had to use a Taylor series to simplify that one. But now we have an equation that we're almost done with. But actually, there's a simplification. Just rewrite. There's a simplification. We're not quite done. I'm just circling it sort of temporarily. But just looking at this equation we've arrived at here, can anyone identify, is there a term in this equation? So if du prime dt equals this stuff, these two terms, is there a term in this equation that's small and that we should drop at this point?
Yes.
Which one?
The second term.
Second term. And what's the reason?
You have a rho prime and a p prime.
Rho prime and p primes. That's nonlinear, so that's small, so we drop that term. That's exactly right. So this term here is small, so we drop it. And so that gives us our final equation, du prime dt equals minus 1 over rho naught dp prime dx. And this is the linearized momentum equation. And then as you can see, basically this is exactly what we would have gotten if we just dropped rho prime to begin with. You get the same answer. Okay, so this is the general recipe that we're going to follow. Basically, we're going to write down our fundamental equation, whether it's momentum, mass continuity, or adiabatic. We're going to write everything as a perturbation relative to the background state. Grind through a little bit of algebra, maybe use Taylor series. And then in the end, we get an equation where every term has exactly 1 prime, and then that's our linearized equation. That's the one that we're going to be able to solve quite easily. Okay, so next, let's do mass continuity. So we had partial rho, partial t, plus u, partial rho, partial x, equals minus rho, partial u, partial x. So we sub in u equals 0 plus u prime, p equals p naught plus p prime, that doesn't matter here. Rho equals rho naught plus rho prime. So we get partial by partial t of rho naught plus rho prime plus 0 plus u prime. Well, I guess I'll write this. U naught is 0. D by dx of rho naught plus rho prime equals minus rho naught plus rho prime, d by dx of u naught plus u prime, that's 0. Was there a question about any notation or anything? Okay, so here's our starting point. And now we get to simplifying. So right away, again, rho naught is a constant number. So it's just 1.2 kilograms per meter cubed. And so any derivative of that constant number is automatically 0. So the derivative vanishes here, and the derivative vanishes there. And so right away we can simplify to d rho prime dt plus u prime d rho prime dx equals minus rho naught d u prime dx minus rho prime du prime dx. Is what we get. So we dropped. So initially we had 1, 2. Well, we had a bunch of terms on the left-hand side. We just ended up with 2. And then now we have terms on the right-hand side. We dropped this. That was 0 because the background state for u is 0. That's it with 2 terms here. Okay. Now, I'll suggest anyone. If you haven't already answered this type of question, are there any terms in this equation that we should drop based on our method?
The last one.
So I heard last one, so this one here, and is there anything else?
The second one.
Second one here?
Yeah.
Okay, that's right. So these two have 2 primes, so we're going to drop these. Drop. Drop. And so we get partial rho prime partial t equals negative rho naught u prime dx. And this is our linearized mass continuity. So once you've done this a little bit, it kind of becomes algorithmic. You sort of get the hang of it. It looks a little bit strange the first time, and sometimes you have to use a Taylor series in the middle. But other times it's just very direct. And I can definitely tell you that either on the an assignment or on the second midterm or on the final, you'll be asked like do a linearization, plug stuff in, drop the appropriate terms, and get the linearized equation. And so understanding this general method is really important. And we're going to use the same approach. This approach, yes.
Sorry, I can't really see what the second term is like after on the first arrow, yeah, right there. So it's like plus, and what is it? Is that u naught?
This is u naught, which I'm just saying is 0.
Okay.
Yeah,
Okay.
because in general, really it's just a 0, but in general you could have a u naught. We're just not treating that here.
Okay. Would we like ever?
Yes.
Okay.
Yeah. You're probably familiar with the idea of like the Doppler effect, right? So like when something is moving towards you, like if an ambulance is moving towards you, you hear the sound become higher pitched, and it's moving away, it becomes lower pitched.
Yeah.
So what the phenomenon there is it's sound waves, but the sound waves are related to motion. And so we will actually in the future include that u naught. And in the ocean also, normally we think of just waves on a calm lake or waves on the ocean, but you could have, for example, waves that are in the Gulf Stream. So the Gulf Stream is a nice strong background current. It flows at 1 meter per second or so, and you could have waves on that moving background, and then that does affect the waves a little bit. So
Okay.
yeah, so I don't know. I'm not sure exactly when we'll get to that, but we will probably do a case where the background is not zero.
Okay. Cool. Thank you.
Yeah. But it's an easier calculation if it is. Okay. So the one equation we've got left is the adiabatic constraint. So finally, do the adiabatic constraint, which was our energy equation. So we had P equals C times rho to the gamma. Okay, so for this equation, there will be another little slight twist, which is that we assume that so what is this constant C? We haven't actually talked yet about what that constant is, and this constant is determined by the background state. So whatever our pressure and density are in this room, you plug in the pressure, you plug in the density, and that tells you your constant. So our background state gives P naught equals C times rho naught to the gamma, which implies that our constant is P naught over rho naught to the gamma. And we're assuming here that this P naught and rho naught are given. So you measure those. Those are your pre-existing background state. And so that fits this constant. And now everything is constrained now. So, so we can write here, so we have P equals P naught over rho naught to the gamma times rho to the gamma. And we plug in P equals P naught plus P prime, and rho equals rho naught plus rho prime. So we get here P naught plus P prime equals P naught over rho naught to the gamma, that's just our constant, times rho naught plus rho prime to the gamma. And so now, as before, we had to do a Taylor series trick. So I'll just pause there for a second. And let people write stuff down. Okay. So, let's simplify the expression. Rho naught plus rho prime to the gamma. So this is a nonlinear term. This gamma is not equal to 1. It's greater than 1.4. So we can do another Taylor series on this. So the first thing I'm going to do is I'm going to pull a factor of rho naught outside of this. So this gives us rho naught to the gamma times 1 plus rho prime over rho naught to the gamma. And then we'll use our Taylor series formula again. So from before, we can recall that 1 plus x to the n is roughly equal to 1 plus nx. I'm not going to go through the Taylor series calculation for that. Actually, it turns out I said we didn't need it, we do need it. So I'm not going to show this explicitly, but you can do this exercise if you want to show that this is the first order Taylor series of this function. And so that tells us that this is approximately equal to rho naught to the gamma multiplied by 1 plus gamma times rho prime over rho naught plus higher order terms. Okay, so get P naught plus P prime, so I'm just going to recopy that down. So P naught plus P prime. On the right-hand side, we have this coefficient, which was P naught over rho naught to the gamma, multiplied by our expansion of this rho naught plus rho prime to the gamma thing, which we said here was rho naught to the gamma outside of 1 plus gamma times rho prime over rho naught. Okay. So something nice happens here. We've got a rho naught to the gamma outside this factor and a rho naught to the gamma in the denominator here. So those are gonna cancel. So this cancels with that. And so we get P naught plus P prime equals P naught outside of 1 plus gamma rho prime over rho naught, which equals P naught plus P naught gamma over rho naught times rho prime. And now a second nice thing has happened, which is that we have a P naught on both sides of the equation, so those cancel with each other. And so our final formula is that P prime equals P naught gamma over rho naught times rho prime. And this is our linearized adiabatic concern. To summarize, momentum became du prime dt equals minus 1 over rho naught dt prime x. Mass became d rho prime dt equals minus rho naught d prime dx. And adiabatic, or thermo, became p prime equals p naught gamma over rho naught times rho prime. And these are the equations for sound waves. In here. Okay. So, so at this point, we basically could go ahead and start solving these equations. And we know that we've motivated this all by talking about sound waves. So it makes sense that we'd look for like wave-type solutions, and that's what we're going to do. But before we actually solve, it makes sense to look at these equations a little bit because there's an interesting combination of parameters that shows up. So the parameters that show up in this equation are the parameters that show up here are P naught equals background pressure, rho naught equals background density, and gamma is basically a gas property. It's called the adiabatic exponent. And that comes from sort of the ideal gas law. Is the green hard to see, or is it okay? It's fine.
Yeah, it's good.
Okay. But there's a special combination. There's a special combination that appears, which is the combination P naught times gamma over rho naught. So let's analyze this. And so anytime you're working with a set of equations and you end up with some like combination of parameters, very often that combination will have some kind of interpretation. And how do you figure out what that interpretation is? A good starting point is actually just to look what the units of it are, or what the dimensions are. So let's ask the question, what are the units, or dimensions, of gamma P naught over rho naught? Well, we can just work it out. So the units of gamma P naught over rho naught are equal to the units of gamma times the units of P naught divided by the units of rho naught. So that's equal to 1. So the units of gamma is a pure number. It's a ratio of, actually, it's a ratio of heat capacities. We don't need to know that. For us, just knowing it's 1.4 is enough, but it's a pure number. And how about the units? What are the units of pressure? Can anyone just tell me a standard form units of pressure?
Pascal, or Newton per meter squared.
Yeah, and those are the same thing. Pascal is unit per meter squared, but I wanted the SI, so that's good.
Okay.
So a pressure is newtons per meter squared. And what are the typical units we use for density for something like air?
Kilogram per meter cubed.
Yeah, right. So kilogram per meter cubed. And so this is newtons per meter squared times meters cubed divided by kilograms, just flipping the fraction. So we can cancel out two factors here, so we get Newton times meters divided by kilograms. And how about a Newton? Can anyone tell me what a Newton is in more fundamental units?
Kilogram meter per second squared.
Yeah, F equals mA, right? So you both said it, so kilogram. So 1 Newton equals 1 kilogram meter per second squared. So this is equal to kilograms meters per second squared times meters divided by kilograms. So our kilograms are going to cancel, as we get here meters squared per second squared, or as I'll prefer to write it, meters per second squared equals velocity squared. So this set of parameters that just happen to sort of fall out of our linear analysis, gamma P naught over rho naught, has units of velocity squared. And so it turns out that this actually is the sound speed. So we're going to do analysis. I don't know if we're going to, how much time do we have now?
15 minutes.
15 minutes. Okay, so we may well get to it. this parameter, this combination parameter says units of a square velocity. And when you see that in any kind of problem, you're given a problem, whether it's about stability of a ship or whether it's about something with waves or whatever it is, if it has units of velocity, it's probably interpreted as some kind of speed, whether it's the speed of a particle, speed of a ship, speed of a wave, whatever. That's not universally true. You can have things that have units that are like velocity, but it really are something else. But in general, if it has units of velocity, it probably has an interpretation as a velocity. And we'll see it explicitly shows up as the wave speed for sound waves. So we will see that this parameter combination is equal to the square of the speed of sound. And so we're going to define C sub s is going to be the speed of sound, so the speed of sound squared. We're going to define that as gamma p naught over rho naught. And if we plug this in, we get 1.4 times 1.01 times 10 to the 5 newtons per meter squared, divided by 1.2 kilograms per meter cubed. And I worked this out. So CS would be the square root of this. And this works out to be 343 meters per second, if you plug in the number. So this is about, 10 to the 5, these roughly cancel, so you get like the square root of 10,000, which is about this number. So the reason that the speed of sound is the particular value that it has in air is because of the gamma factor, which is a property of the ideal gas, the pressure that is at the surface in the atmosphere, and then the density of that surface air. And so right away this tells you that if you're looking at, say, the top of a mountain, where the density and the pressure are going to be different, then the sound speed is going to be different. But in regular situations, like in this room, for example, we get 343 meters per second. Equals gamma p naught over rho naught with the square root factor. Okay. Okay, so I think in the last 10 minutes, we can actually derive what's called the wave equation. Has anyone encountered an equation called the wave equation before? You have, I know. We work on that. Anybody else? It comes up in your earth science, right? It comes up in seismic all the time, very similar equation. So the equation we're going to write down, it also applies to seismic waves, but the interpretations of everything are different. The types of velocities are different. Okay, so this next section is called the wave equation. It is possible to combine our three linearized equations for u prime, p prime, rho prime into a single equation called the wave equation. Okay. So I'm going to say first, note that because we've defined CS squared equals gamma p naught over rho naught, the adiabatic equation becomes P prime equals CS squared rho prime. So our original equation was P prime times P naught gamma over rho naught. We've defined this whole quantity as the square of the wave speed. So we have P prime equals CS squared times rho prime. Let's plug this into our mass equation. So we had d rho prime dt equals minus rho naught du prime dx. And so I'm just going to plug P prime, so I'm going to plug in rho prime equals 1 over CS squared times P prime. So I'm going to eliminate density in terms of pressure. So we get here d by dt of 1 over CS squared P prime equals minus rho naught du prime dx, or dp prime dt equals negative CS squared times rho naught times u prime dx. So next, we will use the momentum equation to eliminate u prime. I realize now, I forgot to draw the line, so I went over, so on the video, something's gonna be cut off. If you ever see me do this, and someone please remind me, I try to remember every time, but I just forget sometimes it screws up the video. Like, I somehow forget between walking from there to there. All right. Okay, so our momentum is partial u prime partial t equals minus rho naught, minus 1 over rho naught dE prime dx. So what we're going to do in the last 5 minutes here is I'm going to call this thing, this is our, we took our mass continuity and we subbed in for pressure. I'm going to call this equation 1, and I'm going to call this equation 2. What we're going to do is we're going to take another time derivative of this equation. So we're going to take d by dt of equation 1. And that's going to give us the second time derivative of pressure equals minus rho naught times CS squared times the mixed derivative with time and space of u prime. Then we've got this cross derivative here, and we're going to eliminate that by taking d by dx of this equation. Then we'll get this du prime dx dt. If we take d by dx of this, we'll get a formula for this thing we can plug in. So then take d by dx of 2, and so we get d squared u prime dt dx. dx dt equals minus 1 over rho naught d squared p prime dx squared. And then we substitute in for d squared u prime dx dt into our equation for d squared p prime dt squared. And so we're basically, we took a cross derivative, we took an x derivative of one equation and a time derivative of another. And so now we have an expression for d squared u prime dx dt, and we're going to plug that in because this is the same expression that appears here. So we're going to get now d squared p prime dt squared equals minus rho naught times cs squared times the right-hand side of this, which is minus 1 over rho naught d squared p prime dx squared. And then this nice thing happens, we get two negatives, the negatives cancel, we also have a rho naught here, and that cancels with this rho naught. And so we end up just getting plus cs squared d squared p prime dx squared, or just writing it down cleanly, d squared p dt squared equals the sound speed squared times d squared p prime dx squared. And this is called the wave equation. And so this equation looks very familiar if you've studied the heat equation before. So if you've studied heat on a rod or something like that, you would have gotten a very similar equation, but only with one time derivative instead of two. The fact that there's two time derivatives actually makes all the difference. It completely changes the behavior of the equation and the interpretation. But the upshot is, so we started with our equations that we wrote down in 1D. We linearized them about a background state. We got three coupled linear equations out of that. We then identified that there was this parameter that showed up naturally that had units of square velocity. And we identified that as that's the wave speed, and we made a calculation, and we showed that we get the right answer, 343 meters per second. And then we basically just did a little bit of a mathematical shuffle game, where we're able to combine our three equations just into one equation for the pressure in this case. And it's just that the second time derivative is equal to a constant times the second space derivative. And this equation contains a ton of physics about waves. So you can get, you might have heard of things like wave reflection, wave refraction, dispersion. All of those phenomena are contained in this equation. Although you might want to think about wave speeds that vary over space to get some of them. But so this equation is super fundamental. This equation ultimately governs sound waves, it governs waves on the surface of the ocean, it governs seismic waves, it governs gravitational waves. Any kind of waves at some level, very likely, this equation is underneath. And so on the fourth assignment, you'll solve this equation. I give you some hints on how to solve it. And then next time, we're going to show that on Thursday, we'll analyze this equation, we'll solve it and analyze the solutions. And what we'll see that lots of normal things that we would call waves solve this equation. And we'll show that they travel at the sound speed, and we'll understand what's the internal structure of a sound wave. So for example, how do pressure and density and temperature, how do they all sort of synchronize in space, and what's happening as waves propagate? So that's for next time. But already, I think you have most of what you need to work to solve the vast majority of the fourth assignment, which is available. Okay, so that's great. That's it for today, and we'll reconvene on Thursday. And as I mentioned, if you have not submitted the third assignment yet, but you would like to earn the points, I don't mind if you take it a few extra days, so please go ahead and do that if you like. And if you have any questions about any assignment, please just let me know, and we can either have a meeting or sort it out. Great, thanks, see you Thursday.
Thank you.